Hello and a very good day. My name is Sariah Khawla, and today I'll be doing Assignment 1 for the Thermodynamics course, which talks about the understanding of the first and second laws of thermodynamics. So, first, we need to go through the overview, which this presentation primarily consists of the introduction, the first law, and then it covers open enthalpy, which is divided into three parts: the enthalpy, the ideal and real gas operation, unsteady state operation, and next we move to the closed system, where we cover the heat and work and its definition. Then we moved on to the second law, which is about the entropy and the reversibility and irreversibility process. Finally, we cover the applications and limitations, and then at the end we have a conclusion. So, firstly, we would like to know how the thermodynamics was introduced to this world. And a quick history of the thermodynamics is when the foundation of thermodynamics was originally found in the 1600s, which is led by Joule. In the 1840s, experiments confirming that heat as energy flows as energy, and in the 1850s, a famous scientist and physicist called Carnot, which is known today as the Carnot cycle, which we will talk about later. Clausius and Thomson's formulating the first and second law, and then around the 1900s, Gibbs introduced the ensemble concept, connecting statistical mechanics by the 1930s. And a few important principles of thermodynamics is when they are the two basic laws of thermodynamics control energy behavior in the domain of living things. In closed systems that are converting, the first law states that total energy remains constant, and then in the second law of the fundamental thermodynamic relation talks about the entropy and the randomness of a process. Uh, Next, we move on to the first law, which talks about the energy conservation, and it's essential to understanding the energy dynamics. To the right, we can see a energy equation, which is said as the total energy, which is equal to the internal energy plus kinetic energy plus the potential energy, which is equal to Q minus W. Q minus W is, as I said, the change in potential energy plus the change in kinetic energy plus the change in internal energy. And then the fundamental idea states that energy of the first law states that the idea is a static object in an isolated system, changing over time rather than generated or destroyed, because as we know, energy can be created or destroyed. This equation can be mathematically stated as I just said on the right equation. It encapsulates the idea that heat and effort interact in the complex harmony to produce any change in the internal energy. So at the bottom we can see two different graphs where when the work is greater than zero, we have an expansion. So when the work is increased, the expansion process leads to a pressure decrease, sorry. And then when the work is less than zero, this leads to a pressure increase, leading to a compression process. Next, we have an open system enthalpy, which is the enthalpy is a major type of energy that flows. The following flow carries across system boundaries in open flow system. This flow, internal energy, and the flow work PV requires to transfer mass over the system boundary makes up the enthalpy. So the work required to transfer fluid mass over the system boundary is known as the flow work. Next, we talk about the second part of the open system, which is the ideal and real gases. Basically, the ideal gas is a thing that we want to assume, which is when the gas behave ideally. So this is all considered theoretically. However, in real gases, which is like how the gases operate in reality, not like how we assume them to work in an ideal gas situation. So in an ideal gas, we have PV is equal to nRT, which is the pressure times the volume, equal to the either the number of moles or the mass of the process to the gas constant times the temperature in Kelvin. And in the real gas, the PV equal nRT is not applicable. So it is essential to comprehend the differences between the ideal and real gases in order to analyze the behavior of an open system, especially when the temperature and pressure changes, as we can see in the bottom graph. Next, finally, for the last part of the open system, we have unsteady state and mass balance of the unsteady state. So when streams enter and depart at the system at different times, this fluctuation states that the flows of the system is deemed to be in an entailed dynamic change, such as the filling of a closed tank with a gas or liquid, resulting in a fluctuation of the mass inside the tank. So that said, there's the mass balance is done on the tank when the conservation of mass is fundamental notion, like energy and conservation. So for a mass balance done on a closed system, or sorry, an open system, whatever flows in is equal to whatever flows out, as you can see in the bottom equations. Next, we talk about the closed system, and the characteristics of a flow system. It suggests that the different types of energy might change inside a closed system. So the total energy can change, sorry, stays the same inside and outside the system. So that said, the system border acts as a either the system border is at either work or heat, and the volume of the closed system is not always constant for the closed system. So, and then for the heat and work, an essential part of this comprehension is the mechanic of energy transfer in closed system. So heat transfer, which is when the internal energy is increased by the increase of work, happens when there is a temperature difference between the system and its surroundings. So the work transfer, on the other hand, occurs when a force operates on the boundary of the system, resulting in a shift subsequent changes by the temperature in the system. As we can see in the bottom graph, whenever heat is done on the system, the Q value is positive, and whenever heat is exiting from the system, the Q value is negative. However, for the case of work, whenever work is done by the system, the positive is negative, and whenever work is done from the system, the value is positive. Next, we have the second law, which covers the entropy. Entropy is basically the fundamental concept of physics and thermodynamics. It is often used as the degree of uncertainty, unpredictability, or randomness in a process. It is the second law of thermodynamics states that the total entropy of a closed system will increase steadily over time. It has several applications to include information theory, sociology, and thermodynamics, contrast to the liquid of solid phase. And this mainly covers the gas phase because the gas phase, as we know, has many particles flowing at different kinetic energy. So whenever the kinetic energy is increased, there's more entropy and more rate of disorder in the system, whether it is open or closed. And then we covered the reversibility and irreversibility of a process. In thermodynamics, when there's a reversible process, it is an ideal situation because the system and its environment may both return to their starting states by following the opposite path, is known as a reversible process. However, this process rarely happens in practice, and it is all theoretical because they provide a baseline to determine the maximum efficiency that may be attained to similar real processes. So there's minimum modifications and the absence of dissipative effects or important effects, including friction and are characteristics of these processes. And once they are excluded, they are considered as a reversible process. However, this process rarely happens in a reality. However, on the other hand, the irreversible process happens when the system and its environment are unable to revert to their initial state. So during restoration, practically every process modifies the surrounding environment. So as we can see here from the bottom, the pendulum, we see that there's the use of potential and kinetic energy. So when the pendulum or the bobbin goes to the highest point, this elevation is known as the potential energy, the change of height. And then when it goes down to the lowest point, this is the highest point of, this is the highest rate of kinetic energy that happens during system, since it's going downward by the pull of the gravitational force to its lowest point and then goes back up to the highest potential point. So there's the use of potential and kinetic energy in this process. Finally, we cover the applications and limitations of both laws. The first law states that there is energy conservation. So in this example, there's the heat is used, and the heat is kind of energy, and thermodynamic processes are governed by the first law. So this kind of law or concept is widely used in the industrial and everyday sector. Such some common examples are the heat engines, refrigerators, pumps, etc. And then for the second law, few appliances or applications used are heat pumps, freezers, these demonstrate practical applications of the second law, primarily also used in the Carnot cycle, which we talked about before, which is talking about the rate of evaporation, freezing, and the usage of pumps and the usage of pumps, evaporators as well. Yeah. And then for the limitations, the first law states that there's, of course, conservation. However, it doesn't explain the feasibility of certain operations or state transitions encountered. For, let's say, for example, we have a heating rod. It doesn't explain how the heat flows from the hot to the cold end of the rod. For the second law, it doesn't have, for example, let's say we have an ambient temperature water in the system in a glass, and it does not naturally cool from the ice cubes. So releasing energy into the surrounding air. The second law speculates that death in which everything is in the temperature. This is because the second law of the degree of the chaos that's and the randomness that happens inside the glass when the ice cube's temperature are released into the glass happens when all the pressure and temperature are the same. So finally, we have the conclusion. So in conclusion, the first law covers the conservation of energy and the basic equation, which is the Q minus W equal to the change in internal energy, potential energy, and kinetic energy. The second law talks about the entropy, the rate of randomness, irreversibility, and reversibility of a process, and which is the ideal situation to choose. And for the history, we have some major scientists that contributed to the thermodynamics to be widely known today, and its many theory and practices used in the everyday life now. For the appliances used or the practical applications used nowadays, these processes are what now very widely used in industry or everyday life, such as fridges, heaters, furnaces, and so on. So basically, the first and second law explain a knowledge of energy dynamics in the macroscopic and microscopic levels, uh, thanks to the laws of thermodynamics. So at the end, these enduring bedrock that mold the understanding of today's people about thermodynamics uh, make a fundamental understanding and explain the constraints and opportunity of thermodynamics in this universe. So thank you very much for listening and have a good day.